In many ways, Flink SQL does a really good job of abstracting away the lower-level details of how Apache Flink does stream processing. For example, it's great that you don't have to manage state or timers yourself. That said, Flink SQL can only properly manage these details for you if it's been given complete and accurate information about watermarks. What watermarks do is to mark the passage of time. Now, we're not talking about wall clock time, but rather about the logical time that is measured by timestamps in your events. While watermarks relate to time, one of their key functions is to let the Flink SQL runtime know when to clean up state that is no longer needed. Or in other words, watermarks trigger garbage collection. Let's walk through an example. Imagine you're using Flink to process a stream of events. Each of these events occurs at a particular point in time. In some cases, you will be able to arrange for your event stream to arrive and be processed in order. When this happens, things are simpler because Flink will always have complete knowledge of the history of your event stream. But it's far more likely that your event stream arrives out of order. When this happens, Flink only has partial information about the event stream's recent past. In other words, if we go far enough back in time, we have seen every event. But for the recent past, we expect there are still out-of-order events that have yet to arrive. Flink only has partial information about this event stream's recent past. In the region labeled Partial Information, we expect more events to arrive. However, for the region labeled Complete Information, we have already seen all of the events. Imagine that you have a requirement to count events in minute-long windows based on the timestamps in those events. Windows always need some storage to keep track of the values they are aggregating. So in this case, where we're counting events per minute, each of these windows is storing a counter. The events currently arriving will have timestamps that place them anywhere in the lilac-colored partial information region on the right. Some of these events may join the 6 events in the older window on the left, while others may join the 2 events in the more recent window on the right. Sometimes one of the incoming events will have a larger timestamp than any previous event. These events push time forward. In this case, our estimate of which part of the stream has complete information has expanded to include the entire time frame covered by the older window on the left. Since this window is now complete, it will report its results, and then Flink can safely destroy this window and free up its storage. In practice, it's impossible to know exactly where the boundary lies between complete and partial information. But the watermark is an estimate of where this boundary lies. Watermarks are generated by subtracting a delay, called the watermark delay, from the maximum timestamp seen thus far in the stream. For example, with a watermark delay of 5 seconds, Flink can correctly handle events that are at most 5 seconds out of order. With a longer delay, you'll be more certain to have complete information before Flink takes action, such as closing windows. But this increased certainty comes at the expense of increased latency. In another video, I've explained in more detail how watermarks are generated and propagated. You'll find a link to that video in the description below. If you have been too aggressive about reducing latency by choosing a watermark delay that is too short, events can arrive late, meaning that the state needed to process them has already been cleared. For example, the event shown here would have been counted as the 8th event in the window that closed after reporting 7 events. But instead, this event is late, and it will be ignored. You may have gotten the impression that watermarks are only for Windows, but that's not the case. All of the time-based operations in Flink SQL rely on watermarks. So this does include Windows, but it also includes interval and temporal joins, as well as match recognize, which is used for pattern matching. I'll have more to say about these operations in future videos. Another parameter you need to think about whenever you're setting up watermarks is the idle timeout. What I'm about to explain pertains to any situation in which Flink is combining information from different streams. This might be 2 different partitions from the same Kafka topic, as depicted here, or it might be streams from different sources. It doesn't matter. Watermarks are initially generated for each partition or stream independently. In this example, the stream from partition 1 is lagging behind the stream from partition 0. Once we bring events from these 2 partitions together, the watermark for the combined stream is the same as the watermark for P1, since that watermark marks the end of the region for which we have complete information for this combination of streams. Now, let's imagine that P1 is no longer producing events. Since P1 is now idle, the watermark for the combined stream is going to be stuck. This occurs because while P1 is idle, its watermark stays in the same place. This in turn causes the watermark for the combined stream to stand still, even though the watermark for P0 is still advancing. In a situation like this, your pipeline will stop producing new results. Whenever this occurs, it is likely that one of your sources has become idle. Depending on your application requirements, you may want to wait until your idle stream resumes, but in other situations, it may be more important to continue producing results without waiting for any missing data. The way to prevent your Flink jobs from getting stuck is to specify an idle timeout. Once the idle timeout has elapsed, the inactive stream is marked idle, and the watermark for the combined stream will stop waiting and resume making progress. A somewhat similar situation can happen when two connected streams, here labeled A and B, are advancing at different rates. In this case, B isn't idle, it's just advancing much more slowly than A. For whatever reason, stream A is advancing much more quickly than stream B, leading to a significant and growing gap between their watermarks. Many operations, such as windowed and temporal joins, wait for watermarks before taking action. As a result, their requirements for state storage grow as more and more partial information has to be buffered. Watermark drift measures this misalignment between watermarks for A and B. As these watermarks drift farther and farther apart, any operation combining the two streams will be buffering more and more partial information, which can lead to significant performance problems, and may also cause operational challenges for the Flink cluster running the job. The way to address this problem is to constrain how large the watermark drift can become by configuring max allowed watermark drift, which you'll find in this section of the documentation on watermark alignment. The effect of this setting will be to throttle the faster stream as needed to keep its watermark within hailing distance. If you're working with open source Apache Flink, you'll need to think about the three factors we've just described. Begin by choosing watermark delays based on your estimate of how out of order each stream can be. This will be 0 if a stream is strictly in order, but for out-of-order streams, typical values range from a few seconds up to about a minute, but can be much longer. You'll want to take care to be sufficiently conservative with your estimate that you won't have too many late events. Then think about setting an idle timeout, so that when streams or partitions become idle, your pipeline won't just seize up, waiting for the stream to resume. And finally, you want to think about how far apart you will allow the watermarks from different streams to drift. On the other hand, if you're using Confluent Cloud for Apache Flink, it will take care of these three parameters for you by observing the behavior of your streams and setting appropriate values. It automatically sets the watermark delay, idle timeout, and watermark alignment for you, ensuring that your pipelines will always make progress and do so efficiently. Confluent Cloud exposes the Kafka record timestamps as a special field called $rowtime that you can always access. The automatic watermarking is defined on this $rowtime field. In certain unusual situations, you will need to provide your own custom watermarks. First, if you have so little data that Confluent Cloud's default watermark strategy doesn't have enough information to determine an appropriate watermark delay. Second, if you require an extremely large watermark delay. And third, if you want to use a timestamp other than $rowtime for your watermarking. Check the description below for links to more information about watermarks, and head on over to Confluent Developer, where you'll find more free content about Apache Flink and Apache Kafka.